Hey guys, Mr. Ainsworth here, and we're going to get into our 17th lesson here, L17, and talk about what's called volume of solids of revolution using what's called the washer method. Washer is just a disc with a hole in it, so keep that in mind. Let's get this right here. All right, that's all a washer is. Now, before we do that, and before I really get into the exact method and everything, I want to show you a little demo here. And let's talk about a solid revolution for just a minute. What we're going to do is we're going to define a bounded region by two functions. Okay, the upper function here is y equals f of x, and the lower function here is y equals g of x. And we're going to consider the region from A to B on the x-axis here. And what we want to do is rotate this axis, or excuse me, this bounded region around an axis. And so let's suppose that we want to rotate it around the x-axis here. What's going to be generated? Well, it's called a solid of revolution because we're revolving it around an axis, in this case the x-axis. So it's going to be a solid with a hole in it. Okay, so let's check this out. If you start revolving the area that we defined here around the x-axis, you'll see it becomes a solid with a hole through the middle. Okay, let me see if I can rotate this for you, see? So it has a very specific shape, and the shape is defined by the two given curves. Okay, once again, let's go back to the beginning here. So you can see how you take a bounded region, wrap it around an axis, it forms what's called a solid of revolution. The question is, how do you find the volume of such a thing? Alright, so let's take a look at that. What we're going to do is we're going to start off with a given function. In this case, I'm using an example y equals root x on the x-axis here. The x-axis here is not drawn, only the root function here, and the y-axis is this way. And what we're going to do is we're going to divide it up into pieces, slices if you will, discs. And in our lesson we're going to actually have a hole run through it too, so we're going to actually use a disc with a hole in it called a washer. But what I want to get at is how we're going to do this. So what we do is we start dividing up into two slices, two big slices, which really doesn't approximate the curve at all, nor does it approximate the volume. As we increase the number of pieces or slices, you can see that it approximates the volume, or the actual volume and the actual curve, a whole lot better as we go from 0 to all the way up to 30 in this case. Notice the true volume is 25,000, excuse me, 25.1327, and here the approximation, just using 30 slices, is 24.295, which is pretty darn good, relatively speaking. Okay, so once again, what we want to do is slice it up into really thin slices, whether they be discs or discs with holes in them called washers, to approximate the volume. And then we have to sum up the volumes and get a good approximation. The best thing we can do is to slice it infinitely thin and then sum them all up, and then take the limit as the thickness goes to 0. That becomes the integral, as you know. And if we know the bounds of integration, which we can find, we can figure out the exact volume, not the approximation. Okay. Let me show you what the solid looks like if you revolve in here. And let's see here. So this one right here kind of looks like not quite a cone, but a like the tip of a bullet. You know, it's round at the top and everything. And its volume can be approximated pretty well by slicing it up into discs. All right. But what we want to do is do it infinitely thin so that it becomes perfect, so that we get the actual volume. Okay, well, let's take a look at that. Okay, so what we're going to do is we're going to take a bounded region right here. And this is the region given. And it's going to be bounded by two functions, an upper function and a lower function. We're going to be given bounds. And then what we're going to do is we're going to revolve it around the x-axis or some horizontal axis or even the y-axis, and or any line parallel to the y-axis, and see what we get. Now each washer is basically a disc with a hole in it. Keep that in mind. So all we have to do is remember how we find the volume of a disk, subtract the volume of the hole within inside it, and we get the volume of the washer. Now each washer is a solid revolution, and the volume can be calculated by the following here. Okay, now keep in mind that every washer right here has an outer radius and an inner radius. So what we want to do is we want to take the, when we take a look at the washer volume, let me change colors here, washer volume. We want to take the volume of the entire disk and subtract the hole. The volume, okay, of the disk, all right, minus the volume of the hole. That's the basic geometrical idea. So what do? We use the outside radius here, which I'm going to call cap R. This is the big radius, the overall radius from the axis of revolution all the way out to the function here. And we're going to, and then again, keep in mind that the thickness right here is going to be some differential of x's right here. We'll call that dx. That's your thickness. And we're going to take the big radius here, r of x, and here's a small radius right here, r, and use those to calculate the volumes. So basically this is a thin cylinder, and to find the volume of a cylinder, it's always base area times height. In this case, the height's the thickness. Just recall that. Okay, so what we're going to do is we're going to take pi times the radius, in this case capital R, squared, times its thickness, okay, in this case dx, minus pi times little r squared, because the volume of the hole is calculated given the small radius in there, times its thickness, which is the same, dx. So both of these involve pi and both of these involve dx. So what I'm going to do is factor out the pi on the left, okay, factor out the dx on the right, and write it as such here. So the washer volume is pi times the quantity big R squared minus little r squared times its thickness, which is dx. Okay, in other words, what I'm saying is it's pi times the outer radius now. Oh, what's going on here? So it's going to be pi times, what's going on? Okay, sorry about that, everybody. What we have here is pi times the outer radius, okay, squared, minus the inner radius, squared, times its thickness now, okay, which is going to be some differential, dx here. That's going to be the washer volume, okay? And what we want to do to get the exact volume, okay, is integrate that, okay, from our bounds, which is going to be given in the problem. So for example, let's say that that's A, and right here, this point right here, on the x-axis here, okay, that's B. We're going to integrate from A to B, from left to right, or from our lower bound A on the left to the upper bound B on the right, of pi, let's bring out the pi, so times the outer radius, which is big R squared minus little r squared, the inner radius, and integrate that in respect to x, and again that's our thickness here. Now this is if the axis of revolution is horizontal. Okay, if it's vertical, then we're going to integrate in respect to y. And I'll show you that in multiple examples. Okay? Alright, so let's get right into it and have a little bit of fun. One thing that's going to be important when defining the volume of a solid formed by revolving a region bounded by two curves is that you're going to have to graph them. Okay? And if you, the most elementary way to do that is by plotting points and go back to basics. Okay? And in respect to your parabola here, the vertex, okay, is going to be at 1, 0. And again, you can simply plot some points here if you like. Plot some negatives, plot 0, plot the y-intercept, just get used to that. So if we plot 0, substitute that in. Negative 1 squared is 1. Plot 1 and you get 0. Plot 2 and 2 minus 1 is 1. 1 squared is 1. You plot these points, 0, 1 here. Then you plot the vertex, and then you plot this point over here at 2, 1. You get your parabola, okay? And your parabola is defined to be y is equal to x minus 1 quantity squared. Okay, that's this function in blue here that I'm tracing. Okay, there's your parabola. Now what you want to do is graph your root function. And the root function, okay, once again, you can look at the domain a little bit here. It's defined to be all reals greater than or equal to 1, because 1 minus 1 is 0, and you can't take the square root of a negative. So we're going to start at 1 here, and then maybe perhaps substitute some values in. So you substitute 1 in, you get the root 0, which is 0. Substitute 2 in, you get 1. 5 in, and so on. If you substitute 1 or plot 1 comma 0, it's here. 2 comma 1, it's right here. And then so your root function is going to be looking like the red function here. Y equals the root of x minus 1. Okay. And notice that they intersect here at 1 and 2 on the x-axis, and at 0 and 1 on the y-axis. Okay? Those are going to be the possible bounds of our bounded region here, which of course is the area between the two curves. Okay, and what we want to do now is revolve it around the y-axis now. When you do that, it's going to look like this representative washer over here, basically a disk with a hole in it. And your cross-section is going to be anywhere in this bounded region, starting at lowest point y equals 0, all the way up to y equals 1, from 0 to 1. The washer is going to exist here. Now, if I was graphing this manually here, what I would do is I would reflect this, and I'd plot some points over here on the left side, like this. In fact, let me do that so you can see what you would do. Okay. Let me put that y value back, or the table back over here. And so let me see, 1, 0, 2, 1. There we go. And I would reflect that over here on the other side. Plot here, same height. 2, 1. Roughly about here or so. And I would sketch both functions so you can draw an accurate graph of them, and then the root function over here. So my other bounded region on this side here, the reflected region would be over here, and then your solid revolution would be revolved around the axis. Again, in this case, the y-axis here. Okay, so representative disk or cross-section would be like so. So this is what it would look like if you're looking at it straight on. On an angle, you would see this three-dimensional figure right here, and if you revolve the whole thing, you get this solid form by revolving around the y-axis. Okay, so the question is, what's the washer volume? The volume of one simple washer, as illustrated in this three-dimensional picture right here. Well, to figure that out, what we want to do is take pi times the outer radius, okay, squared, minus the inner radius squared, and then multiply that by its thickness, which in this case is not dx, it's dy. Okay, that's what it's going to be equal to. The question is, what's big R and what's little r? Okay, well, these right here are represented in our picture here. The little radius, or the inner radius, is this distance, is r, and the bigger radius, let's come down here, is big R. Okay, and we have to find those distances, and these are x values of x now. So what we need to do is solve for x in each function here. So I'm going to take these equations and bring them over here on the right. So if y equals the quantity of x minus 1 squared, then if you root both sides, the square root of y is equal to x minus 1. Now that means that x is equal to the root y plus 1. On the other function here, on your root function, if y is equal to the square root of x minus 1, okay, square both sides, you get y squared equals x minus 1. add 1, I get y squared plus 1 equals x. Okay, now the little r is equal to x, right here on this function here, little r is equal to x, and that's going to be equal to x solved for on the square root function, which in this case is y squared plus 1. So this is going to be equal to y squared plus 1, and the big R, the outer radius, is going to be given by x on the parabola, and x is given by 1 plus the root y. I'm going to write the 1 first so it's not easily seen that it's not being rooted. Okay. So little r, the inner radius here, once again, is going to be y squared plus 1. Okay. So this distance here is y squared plus 1. Whatever that x value is on the x-axis here, it's y squared plus 1. And the big radius here, the outer radius, is going to be 1 plus root y. What we need to do is calculate the washer volume by squaring these radiuses and radii, and then subtracting them, multiply by pi, and then by the thickness. Okay, so here we go. Pi times quantity, big R, which is going to be 1 plus root y squared minus little r, which is y squared plus 1, quantity squared, times your thickness. Now, before we do any integration, we should simplify this, so let's do that. So it's pi times quantity, 1 plus 2 root y plus y minus the quantity y squared, y to the fourth, this is square square, plus 2y squared minus 1. I squared, multiply double square in both binomials. And I want to gather up like terms. So let's see, and distribute through the minus sign. I'm going to have a 2 there, because I distribute through the negative, plus 2 root y. Let's see, plus y. Excuse me, what happened here? Oh, this would be a plus 1. When I distribute through, the 1s are going to cancel out. So I'm going to fix my little mistake there. My little teeny mistake. Let me start over, okay? That's going to happen sometimes, but you know, just as long as you catch your mistakes, you're good. So, and let me fix that other little typo here. This should be y to the fourth. There you go. Y squared squared is y to the fourth. So let me try this again. When the 1s cancel out, so I'm going to 2 root y plus y minus y to the fourth minus 2y squared. There we go. All right, times this thickness dy. And now what I want to do is integrate it. Well, I integrate from my lower bound because the washer started at the low point at 0 and go all the way up to the height of 1. All right, so my exact volume here is going to be the integral from 0 to 1 of pi, and again I'm going to bring pi out, of 2 root y, or y to the 1/2 power, plus y minus y to the fourth minus 2y squared, all in respect to y. I'm going to, once I integrate, I have 2 times y to the 3/2 divided by 3/2, which is 2 times 2/3 or 4/3, y to the 2/3, plus y squared divided by 2, minus y to the 5th divided by 5, minus 2y cubed divided by 3, all evaluated from 0 to 1. And when you get this, what you get is pi times basically the coefficients, 4/3 plus 1/2 minus a 5th minus 2/3. That's what you get when you evaluate at 1. And then minus 0, of course. Everything here evaluated 0 is 0. And when you do the arithmetic and find an LCD of 30, because all these are divisible into 30, you're going to get 29 pi 30ths. And that is your exact volume in cubic units. Okay, so the key on these washer problems is to graph the bounded region. All right, revolve it around whatever axis you want. All right, if it has a hole in it, you're going to have to find your little radius, your inner radius, and your outer radius. Inner radius is little r, outer radius is big R, and calculate the washer volume by using this formula basically right here, pi times big radius minus small radius times its thickness dy, if you revolve around a vertical axis. Find your bounds and integrate, okay? Alright, now that's one thing to say, it's another thing to really get involved, so we need to go through a few more examples here. So what we want to do, in this case, is graph the bounded region first again. So we're going to find a solid of revolution formed by revolving the bounded region, or revolving the region bounded by y equals x squared. So it's a parabola here. So let's graph the parabola. Let's graph it in blue here. Let's say this is 1 here, 1 here, -1, -1. So 0, 0, 0, 1, 1, 2, 4 way up here. So you graph the parabola. Symmetrical about the y-axis here. So y equals x squared here. And let's graph the root function here in green. The root function is defined at x greater than 0, greater than or equal to 0. So 0, 0, 1, 1 is on that graph. And it looks like this right here. It should be curved a little bit more. There we go. They intersect at 1, 1. Let me highlight that intersection point. And the bounded region is the area between them. Whoops. Let me highlight that. And what we're going to do is revolve that around the x-axis. So here's the x-axis right here. Revolve it around the x-axis. So what is that going to look like? Well, let's go ahead and reflect this around the y-axis here and draw the boundary region on the other side so we can see it better. There's the root function reflected around the x-axis here, and let me draw the parabola here. Okay, so we have this bounded region here on the other side. So there's the region reflected. Okay, now when you revolve this region here around the x-axis here, what's going to happen is that you're going to get this solid, and it's going to be the cross-section. Let's take a look at the cross-section here. Is actually going to be a disc with a hole in it called a washer. It's going to have a hole, and the hole is going to be this curved hole. And what we need to do is calculate the outer radius here, big R. We need to figure that out. And we need to calculate the little radius right here, little r. And these are going to be functions of x, because these are heights. And the big R is, some y value. That's some height. And that's going to, that height, that y value, is going to be given by this root function, root x. And the little r here is going to be defined by wherever you are in the parabola. So little r is a y value as well, and it's going to be equal to whatever x is squared. It's going to be given by your parabola function. Okay, and your thickness here is going to be some x differential, which we'll call dx. Okay, so your first of all, in the washer volume, in this case, is going to be pi times big R squared minus little r squared times the thickness, which in this case is dx. So let's take pi times big R squared, which is going to be root x squared, minus little r squared, which is going to be x squared squared, times its thickness. Let's simplify this before we integrate here. We're going to take the root x squared, which is x. We're going to take x squared squared, which is x to the fourth, multiplied by its thickness. So this is the volume of one washer. Okay, and what we want to do is to integrate that, starting here at x equals 0, and it's going to be left bound, all the way to where they intersect, which is at 1. So here are bounds from x equals 0 to x equals 1, because that's where they intersect. Okay, they intersect at 1, 1. So when we integrate and find the exact volume, we're going to go from 0 to 1 this time. Pi, let me pull the pi out, times the integral of x minus x to the fourth times the thickness dx. We're going to get a volume from that. So we're going to have the volume is equal to pi times x squared minus x to the 5th divided by 5. Evaluate it from 0 to 1. That's going to be pi times 1 squared, which is 1. Let me fix that here. Yeah, okay. 1 squared, which is 1, minus 1/5. I didn't do that right. X squared divided by 2. What am I saying here? So it's going to be 1/2, minus 1/5. Okay, minus 0. That whole function evaluated 0, 0 there. And that's going to be pi times 5/10 minus 2/10, which is going to be 3/10. And 3/10 times pi is 3 pi/10. And that's going to be the volume in terms of cubic units here. Okay, so you have one example of horizontal axis revolution, one example of a vertical axis revolution. Now let's take a look at a case where you have to set it up in 2 intervals. Actually, you know what I'm going to do is I'm going to end part 1 of the video here. I'm going to go through 3 more examples, examples 3, 4, and 5, to give you some more experience here. And so go to the second part of my video, the link provided where you got this one here, just below it, and you'll be able to go with me through 3 more examples here to get some more experience on the washer method. All right, see you in part 2.